Hello. In this section, we're going to talk about and review exponential and logarithm function. We certainly have done this before in the previous lessons titled exponential function and logarithm functions, and that's from the functions perspective. And this time, we're going to continue to review those concepts, but also we're going to talk about the if statement in the future, in the near future. Okay, so we know that those are functions, right? So we know its function is a rule that assigns to each input x in domain exactly one output f of x in the range. And we know the vertical line test, we know the definition of one-to-one function and not a one-to-one function, right? And if a function is one-to-one, what can be expected? So we've been applying this property many times over. Increasing function, decreasing function, even odd functions, we have applied them many times. So let's just quickly recap these pairs of functions we have studied, which are exponential and logarithm functions. And for the pair for base 2, we have these graphs, right? Can you mark the points? Can you mark the points, right? So this be 2 to the power x. So can we mark the points to find the correspondence, right? For example, for input at -2 under the rule of 2 to the power x, the output is going to be a quarter. So right here. So these 2 points are corresponding to each other. For input at -1, the output is half. Output. For input 0, the output is 1. For input 1, the output is 2. For input 2, the output is 4. Right? So we have these correspondence. Of course, for 3, 8, it corresponds to this point that we don't need to mark it, you can tell. And this function is, passing horizontal line test. So this is a one-to-one function. It has inverse. And what is its inverse, right? What is its inverse? The inverse is log base 2x, log base 2x. So if you look at these 2 functions, right? One's input, the other one's output. So, okay, so I'm going to bring their tables together after this, right? So first, let's look at the points correspondence, right? The points correspondence is say when input is a quarter, the output is -2. When the input is half, the output is -1. When input is 0, the output is input is 1, the output is 0. And input is 2, the output is 1, right? The input is 4, the output is 2. When the input is 8, the output is 3. So those are the correspondence, right? So we can see their correspondence. And now if we bring them together, right, which we have done these before, right? If we have this picture, right? We have this picture over, and that's for 2 to the power x, and that's for log base 2x. If we bring the 2 pictures together, okay, so I'm going to bring that picture and put it right in the middle, right in the middle, right? And I plot 2 to the power x, 2 to the power x. Right, so let's see what color. Let's use the color green. Okay, you see these 2 curves. They are, if I make the scale comparable, right, they're symmetrical with respect to the line of symmetry, that line of symmetry. Okay, they're symmetrical with respect to the line of symmetry. In particular, you might notice, right? And this, there's the swap of XY, swap of input output we've been talking about, right? It caused the, there's some interesting correspondence between these points. Okay, for example, for 0, 1, which is on 2 to the power x, right? Which is right here, that's the y-intercept. And the corresponding point on the ln on its inverse is right here, 1, 0, right? And you find many, many such pairs of correspondence. 1, 2, right, which is right here, is 2, 1. 2, 1, right? So we find these correspondence, and they're everywhere. So that's the consequence of swapping x and y in the process of finding inverse, right? And we're also reminded of the definition. Okay, let's see. I'm going to bring it to the end, right? The relationship that's between, if you recall, right, the definition between exponential and logarithm function is log base 2 of whatever equals to triangle, okay? If and only if, right, 2 to the power of triangle is equals to omega. Okay, so that's the relationship. That's one is exponential and the other one is a logarithm. So one's domain is the other's range, right? One's domain is the other's range. So in this case, we have learned, right? We have learned that for 2 to the power x, right, and log base 2x, right, if I put these over here, if you look at the domain, one's domain is the other's range. So like the domain and the range. The range for 2 to the power x, of course, is 2 to the power x larger than 0. And the domain for log base 2x is x is larger than 0. You can see this is larger than 0. This range is larger than 0, right? Domain larger than 0, range is larger than 0. And the range for log base 2x is going to be the domain for 2 to the power x, right? You see that correspondence. And there are other interesting facts we have learned, right? If x is approaching negative infinity, right? If x is approaching negative infinity, then 2 to the power x approaching 0 from above 0. If, of course, if x is approaching positive infinity, 2 to the power x is going to be approaching positive infinity. Right, that's not very difficult to recognize, and they have, you know, these are the things we have studied. For 3 to the power x, it's about the same story. It's about the same story. The only thing that's different is that the bases are different, so the details are slightly different. For example, in 3 to the power x, right, we can also easily find the correspondence. Input is -1, the output is 1/3. Input is 1, the input is 0, output is 1, and so on and so forth, right? So very, very similar, and its inverse, right, is log base 3x, and we can also find correspondence between the points. For example, -1/9 is the input, corresponds to the output of -2. Input 1/3, the output is -1, and input 1, output 0, right? So we have these correspondence in similar nature, So if we put these curves together, like what we did before, for 3 to the power x, and bring the two pictures together, we're going to see similar pictures. Okay, so we're going to bring this one over here and put it in between. You can see that points correspondence. You can see the swap, right? And if we plot the picture of 3 to the power of x, okay, and let's see, what color do we want it? The color we can choose to be gold. Okay, so once again, there's that symmetrical feature. And so if I draw a line of draw y equals to x as the it's symmetrical with respect to that y equals to x again, and we still see that correspondence. Okay, x in y intercept here, and that's x intercept there. That you can see that it show up again when x is equals to 1 for 3 to the power x. The output is going to be 3, 1 here, right? When input is 3, the output is 1, which is right here, right? We have that symmetry, that swap of input output as a consequence, right? So these are the things we have done. And once again, if I just simply copy and paste that summary table, it's going to work. All I have to do is just change the base. Okay, all I have to do is just change the base to 3 to the power of x and log base 3. And I just need to change the base. Everything stayed the same. Okay, let's see for e to the power x, which is one of the most important exponential functions you're ever going to encounter, is that look at e to the power x, right? E as a number between 2 and 3, right? So we know the curve is going to be between 2 to the power x and 3 to the power x, right? So we're going to do a series of comparisons as we did before. And let's do some point matching just to refresh our memory. So when input is -2, the output is e to the power -2 right here. When input is -1, the output is right here. When input is 0, the output is 1. Input is 1, its output is e. See, we have all of these very similar correspondence. As x approaching -infinity, e to the power x, of course, once more approaches 0 from larger than 0. This function is going to be used so much in your calculus classes throughout your calculus courses, plural, and going on to differential equation and linear algebra. So this is a very, very important function. So you must know how to graph it. That's the basic you must know. Okay, so as a result that we know this is a one-to-one function, or it's also an increasing function. So it has inverse. And guess what is the inverse? You got it, ln x, natural log x. And this is also one of those singular most important log functions that you are going to encounter many times over in your calculus courses. Okay, so you must know this curve. So you can see with point matching, right? When input is e to the power -2, we get this point, e to the power -1 is right there. And 1, 0. Input is 1, output is in 0. when input is E, output is 1. You see some of these evaluations, like things like these, okay, in your calculus classes many times, okay? You're gonna see some of those for sure. But anyway, let's look at these two functions that are inverse to each other, okay? So when we, excuse me, when we put these functions together, okay, when we put these functions together, right, suppose I put the curves right in between, like what I did earlier, right, you're gonna see the same theme, similar theme, right? E to the power x, and this time I'm gonna make it just red because it's so important, okay? And the line of symmetry, with a broken line right there. Once again, the only thing is different. There's definitely the same S shape and everything else, domain and range. Excuse me. The only thing that is different, excuse me. The only thing that is different is a detailed point can be different, okay? And as we said, the devil's in the details, so you must know the details. For example, the y-intercept in e to the power x and the x-intercept for ln x, right? All these correspondence, they are very, very similar. They're very, very similar. But anyway, without further ado, so let's summarize these functions. As you can see, in terms of domain and range, we have seen these summaries before, right? We have seen this many times over. And now we're going to bring them together, okay, in a different, maybe in a more, you know, in another way of comparison, okay? So let me first finish up this summary, which we are rather familiar with. Okay, so e to the power x, domain and range, they have all these similarities. And so I'm putting this one here, right? And 3 to the power x, we have summarized, right? And 2 to the power x, we have also summarized. We have also summarized, right? And if you can very well establish other pairs like base 3. We have established it for base 3 and base 2, base E. You can easily establish same relationship for base 10, base 5, base 7, and so on and so forth. All of these obey the same relationship, which is log base B of bologna equals to triangle. And this comes to the definition of logarithm, which is base B to the power of triangle. And that should equals to omega. Okay, they're all in this relationship. They're all in this relationship. Okay, so next we've done the graph where we know very well about their pictures, right? We know the vertical line, what we can use for vertical line for, and we will talk about horizontal line. Horizontal line, of course, if you know the output, right? But today we're going to talk about some properties of logarithm, some interesting properties, very useful properties of logarithm. As we know, right, logarithm and exponential functions are tied together. And of course, in this definition, we have a very important requirement about B. B must be larger than 0, and it cannot be equals to 1. Okay, it cannot be equals to 1. So that's the requirement. So this makes the definition. This makes the definition of logarithm definition. So it's also the foundation to set the relationship between exponential and logarithm. Okay, since this is the number one important exponential logarithm functions, and of course, at the same time, we're also studying the other function because they have similar properties. And today, we're going to review what are those properties that we have learned in exponential form. Okay, so suppose that our base is greater than 0 and not equals to 1, right? Or any base. Do you remember that we have learned b to the power of m multiply b to the power of n? And what does this equal to? Have you learned something like this? B to the power of m divided by b to the power of n. And what does that equal to? And one more. B to the power of m and then to the power of n. What do they equal to, if you remember? If you get a little confused about this, right? No fear, no fear. I'm going to show you how you can get those answers just by yourself, even if you forget the formula, okay? If you don't remember, no big deal, okay? You can derive, okay? For example, the first one, right? We know the definition of b to the power of n, right? So b to the power of m is simply b times b times b, how many times? M times, right? M times. So this is done m times, right? So how about b to the power n? B to the power n is going to be, let me make some more space, right? B to the power n is b times b times b, how many times? N times. N times, right? So you just add, you just count how many b's are multiplying itself and ended up with b to the power of what? M times plus n times. So that's going to be m plus n times. Okay. Now, if you're still not certain about this, right? Give yourself an example. To verify. For example, you have 2 to the power of 3 multiply 2 to the power of 5. How about that, right? So 2 to the power of 3 means you're doing 2 times 2 times 2, 3 times. 2 to the power of 5, you're doing 2 times 2 times 2 times 2 times 2, right? This should be 5 times, and that should be 3 times. And together, you get 2 to the power of how many times? 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the power 8 times, and 8 is 2 to the power of 5, 3 plus 5. Right, so that way you also figure out that 2 to the power of b to the power of m times b to the power n equals to b to the power of m plus n. So that we got to figure out. Now you say, what does this have to do with this operation? Okay, just hold on. We'll come back. We'll come back to it. And next, we want to figure out b to the power m divided by b to the power of n. Right? What does that mean? Right? You can also use an example, right? You can also use an example, but this time we're going to do m times, right? So this is m times, m times, and the denominator, of course, is n times. Okay, I'm just doing copy and paste, and so make it easier for myself. So this thing is n times. Okay, so I'm going to use this little convenience for me, right? So this is n times. So you can imagine there's a lot of cancellation going on, right? There'll be a lot of cancellation going on. With those cancellation, in the end, we'll have b to the power of m minus n. Okay, m minus n is not necessarily a positive number. It could be a negative number too. Okay, but in order to figure out, we can use an example once again. Okay, so suppose we have an example, right? If you're not certain, right, you can totally derive this thing by yourself. Say I have 5 to the power of 7 divided by 5 to the power of 4. So what will happen is that on the top, I'll have 5 times 5 times 5, 7 times. 7 times. And the bottom, 5 times 5 times 5 times 5, 4 times. So there are a bunch of cancellation. So in the end, I have just 5 to the power of 3. And 3 is 5 to the power of 7 minus 4. So that way we have derived b to the power of m minus n. And last but not least, okay, certainly these are not last. We're going to have more things to work with. Okay, so we're just working with the power. B to the power m times m to the power of n. What would that be? Right. First, we need to understand what is b. What is the parentheses to the power of n? So this thing is going to multiply itself. How many times? N times. So these are multiplying itself n times. This is n times. N times. Okay, so what do we do next? We can just add up the m, right? Because from the first property we just derived, right? B to the power m multiply b to the power n. So we can just add up the property. We can just add up the exponent. We can just add up the exponent. So we're going to add up the exponent, right? So we're going to have b raised to the power of what? M plus m plus m, right? How many times? Obviously n times, because the n times, right? So these pieces will make that n times again. N times again. There. Okay, so in the end, we're going to get b raised to the power of m times n. Okay, so now we have derived the next property right here. So the property about powers, right? So we're studying these, right? We got these 3 formula, and let's box them for our future use. We derive them. So you don't need to memorize them. We don't need to memorize them, because once we understand their how to, okay, once we understand the how to derive, we really don't need to memorize them at all. Okay. The next ones are B, right? We'll leave it this empty. So we're going to look at something else. Okay. My question to you, what is B raised to the power of 0? What does that equal to? You can pause the recording at this moment to think for yourself. Okay, if your answer is 1, you're right. But if you answer this way, you're still not completely right. You're actually wrong. Why? Because we have to attach a condition that B cannot be 0. B cannot be 0. So these two must be together. Why? Why this condition cannot be left out? I will show you why. Okay, so first of all, when we have B divided by B, we know that's equals to 1, right? By one of the other formula we derived, right? B to the power m divided by B to the power n, right? We know, right? This will be the same as what? This will be the same as B raised to the power of 1 minus 1. And 1 minus 1, of course, that's 0. However, we cannot possibly do these operations if B is 0, right? If B were 0, we cannot do this. Therefore, this can only be possible if we have B cannot be equals to 0. B cannot equals to 0. Okay, so this one has to be attached. This condition must be attached, provided, because we cannot have 0 as a denominator. Okay, we cannot have B 0 as a denominator. B cannot be 0, period. Okay, B cannot be 0 as you know, anything that makes the denominator equal 0, we have to rule that out. Okay, so for that reason, okay, so let me just clean up a little bit. So we're gonna put this property up with our other stuff. Okay, and you guys are, you may or may not be familiar with negative exponents. I assume that you guys might have forgotten, right? Say B raised to the power of a negative n, what would that be? By definition, it is equals to 1 over B raised to the power of n. Okay, this is by definition. So I'm going to put it up there and we're going to look at some examples. You must practice with these. Okay, for example, okay, with this piece, suppose I choose B to be 2 and this to be 1. B is 2. What do you get? You get 1/2, right? So 2 to the power negative 1 is half. So half has another way to express it. By similar reason, what if you have B equals to 3 and n equals to 1? Here you go, you get 1/3. You can just keep going, right? In general, you can have, if n equals to negative, if n equals to 1, and then this B to the power negative 1 is just 1 over B. It's just another way to write 1 over B. And you can practice for a, hey, what if it's negative 2? Right? So what is B is, say n is 2. B is 2. What do we get? We get 1/4, 1 over 4. So you can practice with these exercises, right? So let's look at another one. Okay. What is 1 over let's write it this way, right? 3 to the power of -2. What would that be? You can pause the video, pause the recording and try it yourself. Well, if you look at this form, okay, if you look at the form, okay, and I'm going to put it in this order. Okay, so B is 3, B is 3, N is -2. N is -2. On the other side, it should be B to the power of -n. So from the left-hand side, we have identified N, B is 3. B is 3 for sure. The base is set. Right? But N is -2. So on this side, we're going to replace N. We're going to replace N by -2. So this is -2. N is -2, okay? N is -2. So what would this be? N is negative. N itself is -2. So N is -2. What do we get? Well, we get B to the power of a negative of -2. So that's going to be B squared. Okay, since B is 3, right? So this is 3, what? This is 3 squared. And what is 3 squared? 3 squared is 9. Okay, you can see, okay, you can use this, definition to, the N can be positive, negative, 0. N itself can be positive, negative, 0. So you can write 9 as 1/3 -2. They are the same value, okay? Be sure that you play with these, and the more you practice with these, the better you are going to be. So this is another formula that we have harvested, right? We derive it all by ourselves. Okay, be sure that you work with work with your paper pencil and write it down really nicely and really go through the process. And if you have any questions, please don't hesitate to ask. Okay, and are there other properties? Yes, there are other properties. And one of the other properties would be, say, A times B to the power of N. What would that be? This should be fairly straightforward, right? But still, let's derive it. Let's derive it. And the other property we're going to be talking about is that, of course, we want to derive what this is going to be, right? And the next one we're going to derive is that what if we have a capital A divided by capital B to the power of N? What should that be equal to? Right, so we're going to derive all of these. For example, for that, what does that mean? Well, it just means that A times B inside the parentheses multiply itself N times. Okay, so this piece, okay, so this product is done N times. Okay, so I'm just going to copy the paste here, N times. So among these N times, there are N times of A and N times of B. So as a result, we have A to the power of N, B raised to the power of N, right? Sorry, B raised to the power of N. That's it. So this formula is also handy. Whoops. Handy. How about this one? Needless to say, and this is going to be A times B, A divided by B N times, 1, 2, 3. right? And there are many times in between, right? So once again, it's n times. Once again, it's n times. So in the end, we get a to the power of n over, wait, a to the power of n over b raised to the power of n. Okay, so of course that's n times, right? So we have derived all of these very useful properties. Then you say, what? Of course, we review these properties, and right, we have a reason to. And how does that relate to this thing, right? Which related to the properties. So here, all of these properties is about the exponents, about power. Do we have some properties about the logarithm? The answer is yes. The answer is yes. So these two properties, okay, these two properties, and I'm going to say, okay, these properties, okay, they have something to, oh wait, we have two of these. That's too many. Okay. These fundamental properties, they all have a correspondence in the logarithm form. So we're going to talk about those. Okay, that's what we're going to work on. Okay, so that's what we're going to work on. So the question is, in the exponential form like this, what is the corresponding form in the logarithm form? Do we have a similar property? That's the question. Okay, so now let us take a look. Okay, for example, suppose I have log base b, right? The base is satisfying this condition with a, okay, and multiply a b, and they are together. We multiply these two. Okay, suppose they're all in the domain. Okay, we know the domain is omega must be positive. So A is positive, B is positive. Okay, so provide, so we have a provision, okay, provide. Okay, B is over here, not equals to 1. Capital A is larger than 0, capital B is larger than 0. What would this be equal to? Right, what would this be equal to? Okay, so let's derive that. Okay, so now let's make assumption. Okay, let, okay, log base B of capital A is equals to M, right? So right here, we use this assumption. And log base B of capital B equals lowercase n. What does that imply? What does that imply? By definition, right? By definition, what definition? By definition, what's the definition? The definition is right here. This is the definition, right? So B, capital A, and that capital A becomes, this is a capital A, right? And this is M. So this is M, right? So B to the power M is a capital A by definition. Okay, so from here, we get to there. And what does the other one imply? This piece. What does this piece imply? right? What does this piece imply? According to definition, by definition, right? B omega, so B is omega. So omega is a capital B, right? B to the power of triangle, this is a capital B, right? If you look at this form and that form, and this case is lowercase n, so B to the power of n. So that's how we get from definition. So we get from definition, we get these two pieces. Capital A and capital B are right there, okay? So now let's look at this piece. Okay. Now we have log base B of capital A times B. A is B to the power M. And B is B to the power of N. Okay. And what does B to the power M times B to the power N equals to? Well, we get log base B and B to the power of M plus N. We get to use this property, right? M plus N. So use definition one more time. Use definition one more time. And these two bases are the same. So this piece will be equals to M plus N because M plus N power B is equals to B to the power of M plus N. And here we go. What is M? What is M? M is equal to log base B of A. So this is M. And what is N? N is log base B of capital B. So that's what we got for the product, okay? Log of A times B equals to log base A of capital A plus, not multiplication, plus. So this is the property which is directly, okay, which is directly derived, from what? From this piece. Okay, so for logarithm, right? We have that. So in exponential, we have this. For logarithm, we have the following. So these two are relatives. How about this piece? Right? What does this piece corresponds to? Okay, so let's look at log base B of capital A divided by B. What would that be equal to? Okay, we still make the same assumption. And by definition, we get the same by definition. And then when we apply these into our division case, right? Log base B of capital A is B to the power M. Capital B is B raised to the power of N. So this will be equals to log base B of B to the power of M minus N. So in the end, we get M minus N, and then we just have to substitute M and N in place. So this piece is going to go here, minus log base B, capital B. Okay, so you can see we got these other two properties. And this second property, of course, corresponds to corresponds to the subtraction of exponents. Okay, so these two, okay, these two are connected and these two are connected. And then you say, does this thing connected with something else? And yes, absolutely, absolutely. Okay, so let's see what we get. Let's see what we get. Okay. Okay, so let's talk about what if we have a log base, B, and we have a capital A, and we have a little power. Okay, I'm gonna put this power as, how about just make a triangle, right? What does that equal to? Right? And this time we're gonna make an assumption. We're gonna say, let base B of capital A equals to M. And by definition, we got this piece, right? By definition, we got this piece. And then what do we get? We look at this piece, right? And we have log base B and capital A raised to the power of a triangle. But we want to raise the power of a triangle. But I want to replace A by its equal. A is equals to B to the power M. So I'm going to replace the capital A by its equal. Okay, so that's a log base B and B raised to the power of M multiply the triangle. So once again, by definition, we get the triangle times M. It doesn't matter, the order doesn't matter. And what would that be? The triangle and M equals to this guy. Okay, so what do we get? So in this case, we gotta bring the power. Okay, we can bring the power down to the front of the logarithm. So this is the third very important properties right here. And so these two properties, these three properties are connected. Okay, these two are related, and these two are related, and these two are related. Then you say, how about this one? Then you say, how about this one? What's the use of that one? But this one is really the special case, Okay. This property actually corresponds to something in logarithm as well. Okay, I'm going to show you, and you have seen it, right? Because when we have log base anything, right? As you see in the previous examples we've done, right? If you look at all the log forms, right? Log, let me show you the log. So where's my ln? Where's the ln? Okay, that's fine, log base 2. Okay, I'm gonna make it just a little bit smaller. All right, there. Do we see that this piece, log base 2 of 1 equals 0? Yes. And then we also see log base 3 of 1 equals 0. And we also natural log 1 equals 0. So what do we see? What have we seen, right? What we saw is, okay, log base 2 of 1 is equal to 0, right? That's the x-intercept. And we also see log base 3 of 1 is also equal to 0, right? And we also see ln 1 equals to 0. What do you think? It doesn't matter what base, right? It doesn't matter what base. In fact, log base b, okay, b of course satisfy greater than 0, not equals to 1, is always equals to 0 as long as b is larger than 0, not equals to 1. Okay, so as long as this is the case, as long as this is the case. And where is this come from? You know, what does this relate to? This is related to, you see, because b to the power of 0 is equals to 1 by definition, So this property is related to okay, this property is related to, so these two are related, these two are related, and these are related, and these two are related. Okay, so these are the properties between logarithm and exponential. And what we did here are proof, right? And in the next lesson, we're gonna work on these properties to see how we can use them properly and the common mistakes in using these properties. All right. So let's summarize. Okay, summarize what we have learned today in this lesson, right? We have reviewed about all of these functions, right? Exponential functions and logarithm functions. And in the end, right, we have reviewed all these algebraic properties about logarithm and exponential expressions. In the very end, I like to point out, okay, as we've seen so many examples, b to the power x, right? And so this is in general, right? If b to the power x, and we assume that 0 is b is greater than 0, not equals to 1, b to the power x and log base b, whoops, oh, gee, log base b, I didn't even know how I get that. These two functions are inverse to each other. Okay, their domain and range, one's domain is the other's range. So their domain and range is comparable with what we just did. So in that general form, right? So we talk about 2 to the power x, log base 2x, 3 to the power x, right? Base 2, base 3, base e. What if it's base b now? If we were base b, log base b, right? Base b, base b. Okay, this may be questionable And this may be questionable. Okay, so I'm going to remove these because depending on the base, we haven't talked about the base that's less than 1 greater than 0 yet. So to be conservative, and these two functions, they are inverse to each other, okay, provided that b is larger than 0 and not equals to 1. Okay, so this is the general case. This is a general case. And in the next lesson, we're going to work on applying these properties. Okay, we're going to be working on applying these logarithm properties. Okay, that's all for this lesson. Thank you for watching. Until next time.